All right, hi everyone. So today the topic I chose was the isoparametric inequality, and I guess the main reason is that the solution is it seems pretty obvious intuitively. The solution is going to be a circle, but to prove it is actually surprisingly difficult. And this is actually a really ancient problem. Like supposedly there's a legend that a princess who was escaping a kingdom had to go and solve this problem so she could save her life. So it is, I guess I'll state the problem first. So let alpha be a curve. A simple closed curve. So it doesn't intersect itself, and it loops back to itself. So it's a closed curve. Of length L, and let A be the area that it encloses, or the region it encloses. Then the theorem says that the area is L squared over 4 pi. So this is not a strict inequality. So we can ask about what figure actually optimizes the area. And it turns out the only curve that optimizes the area is the circle. And it seems obvious that it's going to be a circle because, I mean, if you think about the problem for a little bit, if you have anything that is not a circle, we can kind of make local edits on the shape. So we can keep the parameter the same, but we can increase the area. So if you have a shape like this, which is not the optimal shape, and we have a circle, we can see we can keep the perimeter the same, but increase the area by looking locally over here, for example. And if we take a line over here, we can kind of reflect it. So we get something like this. And all of a sudden, the perimeter is the same because we just reflected it. But we now got this new region. So we can increase the area this way. On the circle, I guess we don't have any techniques to locally optimize this figure. So that's why the circle is the most optimal figure, kind of. This is how we got the first proof of this. But there's a problem. The problem is that just because we can't locally optimize a circle doesn't mean the circle can't be optimized. We still have to show that we cannot optimize it. It's kind of like assuming that there exists a solution before we can actually conclude this is the optimal solution. I'll get to that later. But first of all, I just want to present the proper proof for it. So we're going to show the inequality holds, and we're going to show the existence of a solution that actually optimizes it, and when it's actually equal to this area. So before I get to the proof, there's a couple of things we need to, a couple of inequalities we need and a certain formula. So I'll just mention them. So the proof is going to need, the first one is the Amgm inequality. So this states that the square root of A times B is always going to be less than or equal to A plus B over 2. So this is the geometric mean. So that's what that is. This is the arithmetic mean. So you guys have probably seen this before. The second one you guys have definitely seen because we need it in linear algebra. So this is a Cauchy-Schwarz inequality. And this one is, if you have two vectors, you take the dot product. The dot product is always going to be less than the magnitudes of, the product of the magnitudes. And the final thing we need is, the theorem is talking about an area enclosed in a curve. So we need a formula that can get us the area. We don't want to like go in and like find the area ourselves. We need a formula that does that automatically for us. So the area is given, I mean, there's two like slight variations. Okay, so this formula, basically what it's saying, if you have a curve which is parametrized by s, it gives us xs and ys. Then this is our formula for area. If we take the derivative, if we take x times by the derivative of y with respect to x, with respect to s, we integrate over 0 to L, that's going to give us the area. And I mean, we could just take this as a definition of area, but I feel like I should just prove it because it uses Greens Theorem, which we have seen in B42. So these two I think we all agree on. This one is not obvious, at least for me it wasn't obvious, so I'll show how to get this formula. And we need the Greens Theorem for this, so I'll state the Greens Theorem also. So Greens Theorem states that if we have f, x, y, so if you have a function which is R2 to R2, and we have a boundary, which we called, I'll just write down the formula and explain it. If we have a boundary, trying to integrate, we're taking a line integral on this side. On this side, we can just take a double integral over the enclosed region of dv dx minus du dy, and then, oops. So this is Greens Theorem. We can convert a calculation either for a line integral into like a 2D, like a double integral, or we can go the other way. So, I mean, we're going to start off here because we're trying to calculate an area. We're going to do a line integral. And the line integral, I mean, this is kind of like a line integral. So, well, let's see how it happens. So, what we are trying to compute is region R of 1 dA. So if we have this curve, which is alpha, this is the region, I mean, the boundary is going to be this. So this is what we can kind of agree this is going to give us the area for our formula. But now we have to pick our candidates for what is f going to be, because we need an f so we can go back in this direction. So the one condition that we know is that delta v, delta x, u dy equals to 1. So I mean, there's like two really obvious solutions. One is f is equal to x, 0, and then the other one is 0 minus y. And let's think about this just for 1 second. This is going to be our v. The derivative with respect to x is 1. This is going to be 0, so it's obviously going to equal to 1. Same thing over here. This is going to be 0. This term 0. This minus cancels out this minus, so it's a plus. Derivative of y is going to be 1. So these are our two candidates. And so what we are going to do is we're just going to do a line integral over these candidates. And we're going to end up with these two different formulas. So one gives us this one. The other one is going to give us this one. So line integral, alpha is our boundary. F dr. Well, I mean, I'm just going to write 0 to L because L was the length of the curve. And since it's like nicely parametrized, we can just use this formula, dt. So this is like kind of like the definition of the line integral from B42. And once you plug in the numbers, so this is what we're going to get. 0 to L. So we're going to get oh yeah, so alpha is equal to xt, yt. So when we plug it in, we're going to get xt over here, comma 0, dotted with x prime, comma y prime, dt. So this is like a dot product. If we just do the dot product, we got 0L sorry. So this is supposed to be 0x. Let me double check. Whoops. So the mistake I made was like the derivatives are kind of flipped. So this is the actual function. The x goes here because this is our v over here. So this is x. So when you take the derivative, we take the derivative of the y component with respect to x. So this is why this had to be the y, not the x. That's my bad. But so anyway, so that's why this happens. And from this step, you can kind of see if you take the dot product, you're going to get xy prime dt for the formula of the area. So this is equal to that. And the exact same argument goes for this side. If you do it, you get 0 to L minus y 0 dot with the derivative x prime comma y prime dt, which is just going to give us 0 to L of x prime y dt. So this is how we get the formula for the area using Greens theorem. Okay, so now we have everything we need to prove the actual theorem that we want to prove. I'll keep this. Okay, so this proof is both in Schifrin and Carmel. It's the exact same proof, and I think they came up with the proof in like 1940-ish, which is like pretty recent in my opinion, which is kind of surprising. But they've known a proof before, but like this is like the simplest one. So we have to do a construction. So we take a curve. Let me just draw it out properly. This is going to be our curve. It's going to be oriented this way. That's always possible to do. And so let's say that it's arc length parametrized. So this is arc length parametrized. So S is going to be from 0 to L. Okay, so the next thing we want to do is we want to bring two parallel lines from both sides. From this side, we want to bring a parallel line until it's tangent to this side. We want to bring another parallel line which is tangent to this side. So eventually, we're going to get something like this. Two parallel lines, and the tangent at this point and this point. We're going to say this point is when S is equal to 0, because we need to start somewhere, so let's just start there. This is going to be when S is equal to S. I'll just call it S0 for now. The next thing we want to do is we want to draw a circle right below it. It seems weird why we're doing this, but it's kind of clever. So you get a circle, and the circle is going to have a radius of r. So we know how to calculate the area of this. I mean, we have a formula, we have a parametrization, but now we have this circle. So why don't we add both of these areas? If this is area 1, area 2, why don't we add both of the areas, and then we bound both of those areas? Maybe we can have a bound on this. That's kind of the idea. Because with this one, we know it's arc length parametrized. So when we take the derivative, the magnitude of the derivative is equal to 1 because it's arc length parametrized. The advantage of having a circle is if we just take the magnitude, just like the magnitude of the thing is going to be equal to 1. So we have a situation where the derivative is equal to, the magnitude of the derivative for the first curve is equal to 1, and the magnitude of the second curve is equal to 1. So this is like a good situation for us. So that's what we're going to do. And we're going to make use of those two inequalities over there. First thing we need to parameterize this. And the way we're going to do it, we're going to rely on this one. So let me write out the parametrization. So this is our parametrization. This is an R. R is the radius, and like we know a circle isn't exactly a function. So I mean, we're trying to parameterize it like a function. So we have to break it up. We break it up so this top part is kind of like, you can kind of think like we're just kind of shifting these points downwards over here. And I should mention, I forgot to mention this, but our coordinate system starts at the origin of this circle. So this is 0. That's why this formula makes sense. Otherwise, you have to like shift it over. But this is the origin. That's the parameterization for this. And now we know how to calculate the area. So I mean, why not do that? So just on the side note, just so we know where we are headed, if we consider the area of the circle and the figure, we get a plus pi r squared, because we know how to calculate the area of a circle. And if we kind of like squeeze these two figures together, this is like just very roughly talking. Like we get this weird figure here, put a circle right below it, kind of enclose it in a rectangle. And let's suppose these are tangent. So it's like super compressed. The thing you're going to notice, I mean, if the length is L, then there's an upper bound on what the height can be. This height can only be L over 2 because you can only go like up and back. So it's obviously going to be bounded by L over 2. Same thing over here. This is going to be bounded by L over 2. So we can say that this and this is 2R. So what we can say, we have a bound on the two areas is going to be 2RL. And now we're going to use the Amgm inequality, which is going to say that the times it by pi r squared square rooted is less than or equal to half of this sum. So let's write a plus pi. Actually, so half of this sum, I'm just going to skip a step and just write 2RL. This cancels out, which is equal to RL. So, and what is, so we're pretty close. Over here, so what we're going to do next is we're going to square both sides. Pi r squared is less than r squared L squared. This cancels out. So I mean, the final inequality we have L squared over pi. But like this is not the same inequality over there. This one is a little bit like, we want to restrict it even more. But this is like the general idea we're going to do. We're going to add it. On the final step, we're going to use Amgm inequality over here. And then like this is all just going to follow right away because we're going to do this thing about squaring and then dividing by r squared. But we want this to be stricter. We have an upper bound, but we want it to be stricter. And because we want it to be stricter, we have to use a different tool, which is the Cauchy-Schwarz inequality. So now that we know kind of where we're going, this is like the idea. I'll go directly into the rest of the proof. So the area of the figure plus the area of the circle is going to be equal to, these are the formula, this is the formula that I gave at the start of the presentation. It's just how we calculate area. So let's just think about this formula just for 1 second. So this is the parametrization of the top figure. So x and x prime. This is the area, this entire thing, even though there's a negative sign over here, this is the second formula I gave. So this is x bar prime, y prime, so that's why there's a negative. And the bar comes from this parametrization over here. So I mean, they look similar, but the bar, think about the bar is talking about the circle, no bar is talking about the curve. Now the interesting thing is that two of these are the exact same. This is this, is this. So we can kind of like simplify some of the work here. The bar on the y remains because the y's are different. I mean, clearly, one's above the other one. So we have this, but we can kind of see, we can kind of like interpret this as a dot product as xy bar dotted with y prime minus x prime ds. So if you do the dot product, you get this. And now we're going to use Cauchy-Schwarz inequality at this step. Nice thing is we get a possibility for inequality. So that's what we're going to use when we're showing existence. So the next step, 0 to L. Okay, now this is the really nice part. This is why we chose a circle and a figure. This is the magnitude. This is also, x is also x bar. And this is the magnitude of a circle, which I mean is just going to be r. So that's like kind of cool. This is like our derivative. It's not exactly our derivative, but if you think about it, if I just like do this separately, it's going to be y prime squared, x prime squared. Even though this doesn't represent like the derivative of our curve over here, the magnitude is going to be the same magnitude as the derivative of our curve. Well, it's like arc length parametrized. So there you go. It's 1. And then finally, this is probably the easiest part of the proof. You just integrate 0 to L. So you get this. And finally, we have to use one more inequality, which I mentioned before, like the Amgm mean. So we're going to play the same game. And in the final step, we're going to get a pi r squared. And remember, we squared both sides. So it's going to give us RL over 2 squared, which is going to be r squared L squared over 4. And finally, we see that A is less than or equal to L squared over 4 pi. So that finishes part 1 of our proof. So it's cool. I mean, we did have an upper bound, but this actually gives us a way stricter upper bound. And we can actually satisfy this with a maximal, like optimal shape. So now we have to check when does the inequality hold. And this part's also kind of interesting, in my opinion. But now we have to ask questions like, when does the Amgm mean? When does it hold? When does the Cauchy-Schwarz inequality hold? We have to ask these questions. So first of all, we're going to ask, when does Amgm hold? When is it equal? So it usually equals when we're doing like a product of this. This should be, yeah, that's good. So we're taking a product of this. Let me double check. Okay, that's good. So we're taking a product of this, and the only time the Amgm inequality holds is when both of the things are the exact same. That's usually when it only holds, because if you think of it, square root of a times by a is equal to a plus a over 2. So that's like one of the only reasons when it works. So we're saying that the area is equal to pi r squared. Okay, so we have another way to represent the area though. We know that the area the second way we know what the area is, because we're trying to optimize it, we know area is equal to L squared over 4 pi. So this is what we want to show. We want to fit in the figure where this is true. Now, assuming it's true, we realize that the figure that we're talking about, the radius is always going to stay the same, because the figure over here we have, you can imagine if we rotate it, the radius is going to change. But now all of a sudden, if the radius changes, then the area is going to change. But we know the area is constant with respect to r. So that means r has to remain constant too. It doesn't matter how you rotate the figure. Hopefully that makes sense. The r has to be a constant. So it doesn't matter how we rotate the figure. So in our conclusion, we say, as we rotate alpha, radius is going to be constant. Okay, so here's a question for everyone. Is this condition enough to say that the circle, the curve is going to be a circle? So if you think about it, you might have seen the problem before. It seems like a circle is the only object. Like, there's no way. Otherwise, why would wheels be circles, right? We could just take it to be like any shape. So I have these figures. So think about these figures. And then I'll get you the figure also afterwards. I only have 3. So these figures are called solids. I mean, these are solids. We're talking about like 2D. But like these are 3D shapes where the height's always going to be the same, regardless of the way you rotate it. And the construction is kind of neat, because they're actually just surfaces of revolution. And the way how I had to 3D print these ones back, not for this project, this is like before. I just made it for fun. You just take arcs of a circle, you just put them together in this interesting shape. And you can pass it around to Professor Lisa. Yeah, I'll collect them afterwards. So it turns out that this is not sufficient. This is not a sufficient condition to be a circle. So, but we still have some more material to work with. We never talked about the Cauchy-Schwarz inequality being equal. So the second thing we're going to talk about is, when does the Cauchy-Schwarz hold? Well, if you have 2 vectors, v and w, the dot product is only going to be equal to the magnitudes when v is a linear, like a scaling of the other factor. That's the only time when this equality is going to hold. And the way to think about this is that this is actually equal to v w cos of theta. This quantity is equal to this. So obviously, cos of theta is always less than or equal to 1. The only time it's equal to 1 is when theta is actually equal to 0. When it's 0, that means they're just parallel. That's the only time when this is going to be equal. So we use the Cauchy-Schwarz over here. This is where we used it. And I'm going to, I want to finish the proof first, and then I'll talk about the details later on. But what I'm trying to say is that this vector and this vector are multiples of each other. And this one's kind of obvious. This first equation that we have is kind of obvious. if you think about it, remember x bar is also x. And we're saying this is a multiple of this. So x is going to be equal to some multiple of y prime. That's what we get there. Turns out that constant is the radius that we're working with. The second equation is not that obvious. This is the second equation. It's saying that the shifted y is equal to minus r x prime. And why are we shifting this? Because we realize that this condition isn't hold, so we should always go back to the definition of a circle, which means equidistant from a point. And the only candidate for an equidistant point over here is going to be when this coordinate is going to be 0, y 0, for some y 0, because like there's a symmetry on this y, so that's why it has to be in the center. Otherwise, it wouldn't be a circle. So that's what we're trying to do. And finally, when we square both sides and add it together, we get r squared x prime plus y prime. And lucky for us, I mean, it's arc length parametrized. So this is just going to be equal to 1. And we get our final equation, which is the equation of a circle, meaning this is the optimal figure. This kind of shows that the inequality actually holds when our figure is parametrized to be a circle of radius r. So that's our proof. And I still have some time, so I'll talk about the details behind this. So the only time we're saying that these two are going to be equal, and I mean, we already agree that the Cauchy-Schwarz, there is a slight, I guess, subtlety. Just because these two integrals are the same, how do you know that these two have to be like scalar multiples of each other? We know that if they are scalar multiples of each other, this is going to be equal. The integrands are going to be equal, so obviously there's going to be equality. But is there any situation where the integrands are not equal to each other, but the inequality still it's still equal? Like it turns out there isn't, because like you kind of just take the absolute values, and then like the absolute value you can kind of like, I don't want to write it out, but basically if you take this is going to be bounded by if you take the absolute value of the integrand, and the absolute value of the integrand is going to be bounded by this. So we can put in another step in here. But there's only one way, basically, I guess, there's only one way this is equal if the Cauchy-Schwarz inequality holds. That's the only time this is going to be equal. So what we have is xy bar dot y prime x prime, which you get from there, is equal to x comma y bar dot y prime minus x prime bar. So this is your circle. This is 1. This is r. So this side you get r. And on this side, notice that this is bar. Again, this is a unit vector. If this is a unit vector, then it kind of follows that it has to be x bar, y bar is equal to r, y prime, x prime. So this is a unit vector. And if this is a scalar multiple of it, the dot product, we can pull out the scalar out of it, and we're going to have two unit vectors multiplied together. The magnitude is still going to be a unit vector. So we get 1 times it by the scaling factor. And on this side, I mean, this is 1. This is going to be our dot product of the two unit vectors. That's why the constant is equal to r. And this is how we get our first equation, x equals to y r prime. That's our first equation. The second equation, this one, is a little bit more trickier because you have to rotate the figure. But we're going to rotate it by 90 degrees. So we know that this is true. Next thing is we're going to rotate it. So this is our rotation matrix. And we want to rotate it about, it doesn't make sense to rotate it about the origin. So we're going to rotate it about the actual, like the midpoint. So when we rotate it, we're going to have it rotated about 0, y0. So we're going to rotate it about this. We get x, y minus y0. Plus, we have to correct it because like we have to recenter it to the same point. Which is going to be equal to minus y minus y0, x plus y0. And since, remember, the rotation doesn't change the radius, we know the radius is still going to be the same. So finally, we get is minus y minus y0 is equal to r x plus y0 prime. And let me just write it out, then I'll explain it. X prime. Okay. So all of a sudden, this is our x and this is our y. We have this, this is going to be true regardless because rotation doesn't matter. So let's just plug it in. So we plug in this for x, we get this, and for y prime, we plug in this prime. So we do this. This is a constant, so derivative with respect to constant is 0. So we get r x prime, and this is the second inequality we were talking about. So we have this, we square this side, then we get like r squared, x prime squared plus y prime squared, which is equal to r squared. That's how we get the equation of a circle. And that's the proof. So I think I still have a little bit of time, but I'll just talk about the history, I guess. So there's this legend that there's like this ancient princess called Dido, and she, basically her father had 2 kids. He wanted both of them to like inherit the kingdom. When the father died, the brother kind of took over the kingdom, and she married her uncle, but the uncle was like really wealthy. It's like an insane story. The uncle was super wealthy, so the brother killed the uncle, and now she's scared for her life. So she escapes the kingdom and goes to like around Cairo, and moves to like some other kingdom in northern Africa, where she finds a king, and she also helps a bunch of other women escape from like the different places she went. So she had like about 80 women with her, some other guys who left the kingdoms too. She needed a place to live, so she goes up to the king, asking him for a piece of land, and he gave her like an ox hide, which is like this little like piece of like, I guess, like their fur, and he told her, whatever you can enclose by using this oxide will be land. You can take it. So what she did was she like broke it up into like little strips. She like probably glued it together, and then she had to face the isoperimetric inequality. She was like, how do you optimize this? And supposedly she solved it, but like at that time it wasn't more mathematical. It was like she was trying to like not die. And then later on, ancient Greeks also dealt with this problem. They thought they solved it actually because they were working with only polygons, and there is a systematic way of checking every polygon. First, you show that every regular polygon has more area than just any arbitrary polygon, and next you show that a circle of the same perimeter has a greater area than any regular polygon with the same perimeter. And it's not too hard to show that actually, but I'm not going to talk about that. The next person I want to talk about is the first time we made any actual advances in this problem, which was by Jacob Steiner in 1842, which is, I feel like, is really recent. And he kind of followed in the steps of Descartes. So Descartes kind of brought like geometry, he was bringing algebraic equations into the thing. So he thought maybe I'll approach it somewhat algebraically. And he found 5 different proofs, which is insane. A single person found 5 different proofs of the inequality. The problem was he was doing the local editing that I mentioned initially. He wanted to go locally into the figure, show that you can optimize the figure, and show that you can optimize every single figure that is not a circle. So he's like, therefore the circle has to be the greatest, has to have the greatest area. there's a flaw. He assumes that there's existence, but like, doesn't it exist? Isn't it kind of obvious? I'll talk about that later. There's a guy named Weierstrass. I mean, Weierstrass, M-test, you probably heard of from like different class. He was also editing his work because like there's a problem with like translation between Steiner's work, and Weierstrass was a German. He had a German translation of the thing, but then problem was that when there was a translation, there was a lot of errors that were introduced. So he went in, fixed a lot of errors, and I'm guessing he really enjoyed the problem and he hated Steiner or something. So he developed this theory called calculus of variations. And isoperimetric equation it just like kind of pops out of it. It's like a really strong theory. This is like a kind of like a simple problem compared to the problems that he was working with in his theory. But the theory is it's too complicated. The proof for isoperimetric inequality is like kind of like a corollary. It's going to take you some time to understand it. So people still try to find an elementary proof for the thing, and there's a lot. Now there's actually a lot. There's like, I found a paper online, and I saw like 5 or 6 different elementary proofs. So one of them was by this guy named Schmidt. That's the proof I just presented. He came up with this elementary proof. Super clever, in my opinion. Like, I tried playing around with it, but like there's not much to play around with. Everything is just so perfect. Even the formula, there's 2 different formulas for areas. He was very selective of the way he chose the 2 formulas. It just so happened to work out. So the final thing, I wanted to talk about some calculus of variation. Well, that's okay, it's fine. I feel like this is interesting enough. But the last thing I guess I want to talk about is I want to give a proof of Steiner's, like one of Steiner's proof, because they are very nice. Hopefully we have time. It's not that bad. If you know Euclidean, if you've done Euclid's geometry, like the subtended angles, all that stuff, you're gonna think to yourself, how come they didn't come up with this proof before? So this is Steiner's 4-hinge proof for showing that the circle is the optimal figure. So he's saying you start off with any figure. That is not a circle. So let's say the figure looks like this. I mean, I have a specific intention. That's why I drew it like this. But obviously, if you let this being the starting point, there's going to be some point along the perimeter where the 2 perimeters, like the perimeter is divided in half. Let's say it's over here. Next thing you're going to do is you're going to cut this figure through the perimeter. And now I claim, or Steiner claims, that the top area is equal to the bottom area. Because suppose it isn't equal. Well, then we can just reflect this to the bottom. The perimeter stays the same, and we get a figure with a larger area. So that means the areas have to be the same. That's the first point. Even though it might not be symmetric, the areas definitely have to be the same. That's what he was saying. So next he's saying pick one of the halves. So let's say we pick the top half, which is not a semicircle because we assume like it's not a circle. So we can definitely get we can get a half. We can definitely do like, we can cut the perimeter so the top half is not it could be a semicircle in the bottom, but we can get a top half which is not a semicircle. That's what he's saying. Assume this is not true. Well, there's an interesting property about semicircles. So if I take this, this angle is definitely not going to be 90 degrees. And the reason is in Euclid's geometry, there's like a lemma where if you have a semicircle, you draw something like this. This is always going to be 90 degrees. And it's an if and only if condition. So it's a semicircle if and only if every single point of this makes a 90 degrees over here. If it makes 90 degrees, then it's also a semicircle. It's an if and only if. So this is definitely not a semicircle. I can find a point where the angle is not 90 degrees. I take that point, and now I'm going to keep these pieces the same, because I can't change it, otherwise the perimeter might change. I don't want to deal with that. But I'm going to change this length a little bit. I'm going to change it to the point. I'm going to bring it in a little bit. So this angle becomes 90 degrees. So finally, we got a figure like this. And we're considering this figure. It might not be smooth. It might not be like super nice. But he's arguing that this figure has the same perimeter, has a larger volume. And the final piece of the proof, I mean, you guys might see it. The final piece of the proof is showing that this has a larger area than this. So the way we show that, this is 90 degrees. This is the same as this. These two are the same here. So, like, we don't have to do anything too formal. I mean, the height here is going to be definitely larger than this alpha. We could do like sine of this angle. I mean, this is not 90 degrees, so this height is definitely not going to be the same as this. So this triangle has more area than this. These two areas are still the same. This is the same. This is the same. This one is greater than this one. We can reflect it, and all of a sudden, from a curve that wasn't not a circle, we constructed another curve which had a greater area. This was Steiner's one of his like 5 proofs, and all of his proofs are kind of like this. They're like very simple. And just one quick thing, why can't we assume that the circle is not an optimal shape? For what reason? I mean, if we take a circle, there's no way we can do this argument on this. There's like no half where the top is not a semicircle. So there's like, what we can say is a circle is definitely a candidate for being the optimal shape. Well, we still have to prove it's an optimal shape. And there's a problem of existence. And it is kind of subtle, honestly. I found a joke, which I'm going to tell you guys, somebody made about this problem, and it kind of highlighted what the main issue is. So I don't know who made this joke. But the joke is like, Steiner said that if you take any figure, I can optimize it so that there's another figure, I get another figure which has larger area. So if I have figure A1, I can optimize it into A2 so that the area of A1 is less than area of A2. Now if I take a circle, if I try to optimize it, I'm going to get a circle once again. Therefore, circle is optimal. The joke somebody made, I kind of found it funny. They were saying we're going to find the largest integer. So if I give you any integer which is not a 1, so for example, you give me 2, I can optimize it by squaring it. For if you give me 5, I can optimize it by squaring it. So definitely I can optimize it. You give me a 1, I square it, it's still the same number. So therefore, like 1 is the largest. 1 is the largest natural number. That kind of highlights the issue with this thing. You're assuming, if you assume there's a largest integer, and you show that every single integer is not the largest, then the one that's remaining has to be the largest. That's the flaw with Steiner's argument. Yeah, so this kind of highlights what the issue was, and then it took a lot of time to resolve the issue. There's an entire branch of mathematics called like calculus of variations. It deals with, you think about, instead of giving functions like single points as inputs, you're giving them functions. So the functions are called functionals, and you're giving functions as an argument to functionals. And the study of that is really related. I was really surprised. There's a lot to do with physics. General relativity has a lot of stuff with it. So it's really interesting. And from what I've read, apparently there's a lot of stuff that hasn't been done. Like there's a lot of stuff that hasn't been like fully studied completely. There's only a specific type of functional that they usually consider, which is like an integral. But yeah, it's something interesting if you guys ever want to go out, want a summer project or anything. Like calculus of variations is a pretty good topic to study. And yeah, that's my presentation. So do you guys have any questions?
Yeah, I wondered why it took so long before this fact appears to have been known since probably the Greeks, but why did it take so long before there was a rigorous proof?
That's a good question, and from what I've read, people have talked about why it took so long. They think the main problem was that people didn't realize that the existence was actually part of the problem. That's what really kind of impeded mathematicians, is that they never recognized the problem with existence to be part of the same problem. They're like, there's no way the solution doesn't exist. So that's probably what I guess distracted them from solving the problem. So, yeah. Sure. So this we get, however we don't ask, because it can be parametrized somehow, arc length parametrized. And the way we're getting this one is, I'll connect the half here, half here. So we have an x-coordinate for this point over here. Basically, the idea is that we are going to get every single when we're traveling this way, we're going to go across every single x-coordinate from here to here. So that's why we can just use the same, since we're already covering all the x-coordinates from here to here, we're just going to use the same x-coordinates here. This equation is just the equation of a line, kind of solved out for x, or solved out for y, sorry. So we have an x-coordinate. We know that this point, eventually S is going to get to such a point where alpha is going to have the x-coordinate here. We're going to go down here. We know what the x-coordinate is. To solve for this point, the y-coordinate over here, we can just work the equation of a circle backwards. That's how we got this. Yeah.
Parameterization of a circle won't necessarily be a arc-length parameterized.
That's correct. And